last section, we will introduce the quick measurement function, because after the device data fitting and data processing automatically executed here, and also the data device diagnose here, we don't need to do any frequency swap, because we already know where's the specific resonance frequency for the specific device. So we can go to much quicker measurement without swapping the device, which can increase the measurement speed a lot. So we use it by click this. Because now we can see the relay wave amplitude analyzed window have been disappeared, and the frequency swap have been stopped. It only show the fixed frequency, the phase change at the fixed frequency position. So now the measurement, you can see the measurement, the date sample rate have been increased a lot here. So during this quick measurement mode, we will demonstrate another feature of our device, which is the temperature compensation function. Now we are doing a temperature compensation demonstration. The temperature compensation is important because we use the very high piezoelectric coefficient substrate to enhance the device sensitivity. But the high piezoelectric coefficient substrate also they are also very sensitive to the temperature. So this will make the difficulty for distinguish the phase change between mass load and temperature drift. So we need to remove this temperature drift effect from the final measurement result. So firstly, we are showing how bad is the temperature effect on a real device. So we just simply put a finger onto the device. See it. Here we can see the temperature drift caused by our finger to the device seat, which caused the first order love wave transmission coefficient phase reduced, and the third order love wave reflection coefficient phase increase. Now we removed the finger, the temperature will recover back. We can see both the first order love wave transmission coefficient phase change recovered, and the third order love wave reflection coefficient phase recovered. We waited for a moment. Then we will engage the liquid onto the surface to prove that the first order love wave is always sensitive to the liquid contact, but the third order love wave resonance is independent with the liquid contact. Now during the temperature recovery, we will add the water drop onto the surface to prove that the first order love wave transmission coefficient phase change is sensitive to the liquid contact, which is the mass change onto the surface, but the third order love wave reflection coefficient phase change is independent with the surface mass change. Now we put the watt drop or okay. Now the watt drop engaged. Okay, we can see here the first order love wave transmission coefficient phase have been reduced, but we rarely see any phase change on the third order love wave reflection coefficient. So let's see what happened when we removed the watt drop. We just use the tissues to absorb. Now the watt drop have been thoroughly removed. Now we can see when we remove the watt drop, the first order love wave phase change have been recovered. This step shows the mass load effect on the surface, which will be the antigen antibody binding process on the surface in the future. But on the third order, we can't see any change during the mass change. So by simply subtract this first order love wave resonance to the third order love wave reflection coefficient resonance, now we can get a purified mass change signal only here. So we will not repeat this process to save some time, but it's already proved. All of device, we don't need any temperature sensor, but we can separately detect the mass load change and the temperature change, which is very fundamental to high performance surface acoustic with biosensor, which use the high piezoelectric coefficient substrate. So that's it. Thanks.